Welcome to Study Loop.
All right, so problem number 59. So problem number 59, part A states, the wave nature of particles results in the quantum mechanical situation that a particle confined in a box can assume only wavelengths that result in standing waves in the box, with nodes at the box walls. Use this to show that an electron confined in a one-dimensional box of length L will have energy levels given by E sub n is equal to n squared h squared over 8ml squared. So basically what we're doing is deriving the equation that we have been using for most of the problems in this book, in this chapter, in this section. So let's start with, what we know about this. So for a standing wave, or for a particle in a box, like it says, it can only have standing waves with nodes at the walls. So what that means is for n equals 1, it's going to have one node, it's going to have two nodes, one at and one crest, one hump at the center. For the n equals 2, it's going to have two nodes at each, and it's going to have two crests, two humps. So for n equals 3, it's going to be something like this. Okay, so what can we say about the wavelengths of this standing wave? So for n equals 1, it's easy to see the wavelength is equal to 2L. Because the full wavelength would have to be, to continue on, you get a full wavelength. So it would be back and forth. So or for n equals 2, a full wavelength is equal to L. For n equals 3, a full wavelength is equal to 3/2 L. So from that, we can state that the length of the box is going to be equal to n lambda over 2. Where, like I said, for n equals 1, so, or n lambda is equal to 2L. So for n equals 1, lambda is equal to 2L. For n is equal to 2, lambda is equal to L, so on and so forth. All right, so from this relationship, the next thing we need to know is we need to know the de Broglie wavelength. So the wavelength of a particle with respect to its momentum. So lambda is equal to h over p. Or solving for p is equal to h over lambda. Now, classically, non-relativistically, momentum, p, is given by mass times velocity, and the kinetic energy is given by 1/2 mv squared, mass times velocity squared. So we can now plug in, we can now solve p in response to mv. So let's say energy is equal to p squared over 2m, because if you plug in m squared v squared divided by 2m, you get energy. All right, so now we can plug in what we know about the de Broglie wavelength, the momentum. So this is going to be equal to h over lambda squared. Let me rewrite that a little bit more clear. H over lambda squared over 2m, which is going to be equal to h squared over lambda squared times 2m. Now we know lambda is equal to 2L. So we know lambda is equal to 2L over n. So if we plug that back in here, we get 2 squared is 4. Yep, that makes sense. So we get the energy, E sub n, is equal to h squared. I'm just going to do this one step at a time so you can kind of see how everything works. H squared over 2L over n squared times 2m, which is going to be equal to n squared h squared over 8ml squared, QED. So that means we have derived what we wanted to, the expression that we wanted to derive from the beginning. All right, so that is part A. It's all right. A. Now for part B. If a hydrogen atom is modeled as a one-dimensional box with length equal to the Bohr radius, what is the energy in electron volts at the lowest energy level of the electron? Okay, watch with this problem. When I first read it, I kind of thought that it was wanting to model a hydrogen atom. So I was trying to use the mass of a hydrogen. So don't do that. It's mass of it where it's an electron on a hydrogen atom. So it's the mass of an electron. Just, I guess, yeah, just kind of pay attention to that kind of thing. So for B, if L is equal to A0, which is the Bohr radius, which is equal to 0.5292 times 10 to the minus 10 meters. This is given in your book under the appendix, under the constants. So the ground state energy then, E sub 1, is given by h squared over 8ml squared, which is equal to 6.626 times 10 to the minus 34. Oh, can't forget units. Units are always important. Joule seconds squared divided by 8 times the mass of an electron, 9.11, times 10 to the minus 31 kilograms, times the Bohr radius squared. So 0.5292 times 10 to the minus, not 20, to the minus 10 meters squared. Working through all of this math, you get 2.15 times 10 to the minus 17 joules. And if we want it to be in electron volts, multiply this by 1 eV over 1.6 times 10 to the minus 19 joules, which is equal to 134 electron volts. Now, this is a huge over approximation because what we know is that the ground state energy for hydrogen, electron hydrogen, is equal to 13.6 electron volts. So it's basically an order of magnitude, a factor of 10 off. But, you know, it's a start. Okay, that's that. That's the problem.